second example is motor service. Right now we have three discrete inputs: start, reset, and stop, and our program is going to enable us to control these two outputs, motor and service light. Again, we have 5 requirements that we need to fulfill in our program. Requirement number 1, motor will start when start, which is normally open moment, is pressed. It has to remain on when start is released, so latching requirement. Anytime stop, which is normally closed, is pressed, the motor will stop. So in the first 3 requirements, it's a simple start stop motor example with the latching requirement. Requirement number 4, that's the new part that involves timers. Service light will energize if motor has total running time of 10 hours, not necessarily consecutive, indicating maintenance is requirement on that motor. The last requirement, only when maintenance has been completed, the service light can de-energize and the timer will reset when the maintenance crew press the reset button. So similar to the previous example, it's a mixture of discrete IOs with timer requirements, and in order to successfully integrate the timers, the same thing, we need to specify on how many timers we need in this solution and the timers type. So for number of timers, all what we have to look for is the timer delay values that we have. So in this example, we only have 10 hours, so this is an indicator. We need to go with 1 timer to fulfill this requirement. The second thing is what's the best timer type we can go with to fulfill this requirement. So one more time, we have 3 timers, TON, TOF, and RTO, and to decide which timer is easiest to go with, all what we have to go for, we need to go with the requirement that involves the timer delay values, and we need to look at the key terms on, and this is going to help us to decide TON, TOF, or RTO. In this example, it says the service light will energize if motor has not necessarily consecutively run for a total running time of 10 hours. This requirement, anytime you come across this requirement, total running time or total operation time or not necessarily consecutive, this is an indicator it's easier to go with an RTO timer to fulfill this requirement. Now let's see the RS Logix implementation for this one, and we'll go from there. Any solution has to always start with creating the tags. So in this program we have start, stop, reset, motor, service. All these are Boolean tags, and T1 is the only timer that I'm going to use, which is of timer day type. Let's go ahead and start building the solution. So in the first rung, it's a simple start stop motor, which we have done before several times. That's why I will just pretty much go through it quickly. So the first XIC is for the start. It's going to start the motor, which is an OTE, and in between we have the only condition to stop it, which is an XIC referring to stop, and of course the latching requirement, which is nothing but an XIC instruction referring to motor, the same output. Anytime we let go the start, this path will take over and maintain the rung for this one. Now the second rung, we need to trigger, I'm sorry about this, to create a new rung. We need to have our timer, which we decided to go with the retentive timer. We said it's easier to go with this one. Now what's the condition that's going to start this timer? Is motor itself, because remember the requirement says the total running time for motor. So anytime the motor is 1, I need the timer to start, so I'm going to use an XIC instruction referring to motor. And in the RTO, the name that we have created in our tags is T1. The preset value is 10 seconds, so I'll just grab a time calculator. So 10 hours, so that's 10-0. To convert to minutes, that's times 60. To convert to seconds, that's another 60. And remember in Albrad it's milliseconds, so we need to have 1000 milliseconds. So it turned out to be a nice number, 36 millions milliseconds. So 36000 36. Why it's not printing? That's good. Excellent. And what will happen after the 10 hours time is reached? So one more time, new rung. The done bit is the timer delay condition that will trigger our service light. And since we're using a retentive timer, remember there's only one and only one way that you can reset a retentive timer, and that's using a reset instruction. So for the same place we used to insert our timers, where TON, TF, RTO, at the last option is the reset instruction, and according to the requirement, the reset input is the one that's going to do the reset. So here you go, reset instruction, the next IC, and resetting T1. Now that's the solution. Let's see this actually, if it works. So downloading, no errors to show, that's a good thing. It's in run mode right now. So right now pressing the start. You can see right now the XIC instruction is true. Logic continuity across the rung. Motor is on. Motor is on. The RTO timer is on right now. Anytime you let go, that's no problem because the latching is taking over and maintaining the motor and timer on. Anytime I decide to hit the stop, it's open right now. The XIC instruction is false. Breaks the rung. Motor is off right now, and the RTO is disabled right now. But as you can see, since we are using an RTO, the accumulator is retained. So anytime you let go the stop and you decide to hit the start again, the motor is on and the RTO resumes timing from where it stopped. And that's the advantage and the easy way using an RTO when the requirement is to calculate the total running time for a device, in this case the motor. Okay, so one more time, it stays on. I'm going to speed things up so that we do not wait for the full 10 hours. So I'm going to go to the accumulator and bump it to 36, 1, 2, 3 zeros, 1, 2, 3 zeros. And what happens right now it's done. The service is on. And the only way, if we decide to hit the stop right now, the motor is off. But as you can see, the service is driven by the down bit of the timer. So that's why it stays on all the way. Okay. Right now, the only way that I can actually reset the service light and the timer is by pressing the reset input. So pressing reset, you can see that the left side it's closed right now. This is true, and the reset instruction is activated, and the accumulator for the timer goes down to 0. And that's the solution for this one. So one more time, let's run it. So start, let go, it's starting, bump this to 36 million. Service light is on. As you can see right now, something really interesting is if we stop the motor, it stops. Okay, but if you decide to start again, it will start even though the service light is on. And that's actually not, they did not mention this in the requirement of the problem that we are solving. However, since I do have the solution right now, I'm going to add an extra requirement, which is very common in industry. Basically, anytime, depending on the device and the application that you're dealing with, if it's really critical that you do the maintenance before you are able to start the device again, we refer to this as locking the device, the motor. In other words, if the service light is on, I do not want it to stop the motor. However, once the motor stops, if the service light is on, I want to make sure I cannot restart the motor unless it has been serviced. Again, it depends on the application. It's not among this requirement, but since we have the solution, I will just implement it right now because it's simple modification to what we have right now. So let's see how this one actually works. Now the only requirement that we need, the only modification we need to do to fulfill this locking requirement so that if the service is on, the motor cannot be restarted, is by adding a permissive condition next or in series with the start. This will be an XIO instruction referring to service. Now let's see how this actually is affecting the program to fulfill this requirement. So when the service is on, it will not turn off the motor. However, it will lock it from being restarted. Now let's see if you hit the start, I let go, it takes over, the motor is on. Now look what's going to happen once I bump this to the preset value. The service light is on. This, for the time being, did not affect the motor. The motor is still on. However, anytime legitimately you decide to stop the motor, you stop it. Okay, but as you can see, the permissive condition right now we have added is false right now. So if I try to press the start right now, you see this condition is creating a gap in our rung and the motor cannot restart. Again, it depends on the application. If the requirement requires that you want to lock an output, that's a common way to do it. So right now, the only way in this architecture that I can actually trigger the motor one more time is by hitting the reset first. By resetting the timer, this goes to 0, the service light goes to 0. Now the XIO instruction is referring to a 0 service because it's off right now. This is true. Right now, if I hit the start again, logic continuity and everything starts the same as before. So here you go, locking requirement.